then figured out, again using just first wave techniques, it figured out how to break into that, what an attack would look like. It wrote a program and embodied it in some data that it then sent over the wire to this other machine to get into it, and was able to break into this other machine and capture a flag, steal a piece of information from this other machine. A third machine saw this movement take place, thought that there was something funny about that packet of information. It took that packet of information, it analyzed it, it discovered what it was trying to do. It discovered that it also had the same vulnerability and will be susceptible to that attack. It figured out how to repair itself. It wrote a patch for itself. It applied the patch for itself. And so when it got attacked, it was now secure. That whole thing took 20 minutes. Like, the speed in which that was taking place was just phenomenal. I mean, so it was really exciting to see this. And people are now continuing to develop these cyber reasoning systems and using them to help do things like build defenses for the electrical grid and things like that on a national level. So, mathematics. Here's a piece of mathematics that you might not have studied, called mathematical logic. So you may have studied the notion of Boolean algebra. Who's come across Boolean algebra? Okay, a bunch of you have come across Boolean algebra. Now if you take that up a couple of notches and think of that algebra as a structure in which you study the nature of the operators themselves on it, you come into an area called mathematical logic. And mathematical logic turns out to be tremendously rich. So it has notions like conjunction, disjunction, and negation that you expect from Boolean algebra. It has De Morgan's laws. It has the operator implication, where one thing, one statement might imply another statement. It then has other operators, these are called quantifiers, which said this thing is true for every value, or this thing, there is a value for which this is true. And so when you're doing math proofs, you'll often say, for all values such and such, here's a theorem that works for all of these values. And mathematical logic captures that notion of being able to reason about those sorts of things in a structure that you can itself study mathematically. So you can identify what kind of theorems can this logic thing express, what kind of theorems can this logic thing be able to prove, and you can ask mathematical questions about completeness about it. And there's been tremendous work, particularly in the last 20 years, of developing logic solvers that will take huge statements in mathematical logic and simplify and reduce them to get to an answer. Intel has been working on this again for 20, even 30 years, to be able to specify the behavior of their microprocessors. And so you may have some inside a chip, it's doing lots of logic with bits, essentially Boolean logic, but you may want to be able to describe under what circumstances will all of that be correct? Will I get the answer that I want, and under what circumstances will I fail? And they end up writing theorems or writing hypotheses, lemmas, that they want to be able to prove that these things, the lemma itself, can be 5 gigabytes, 10 gigabytes long, just to state the property that they want to prove. Like humongous. So imagine that you had, what a gigabyte is like a full textbook, something like that, approximately, roughly speaking. Imagine you have one theorem that takes a full textbook just to write the statement of the theorem. Okay, that's the kind of size of thing with the complexity of microprocessors that we're dealing with. And now we have logic solvers that can crank through those things and be able to say, here's a case in which it fails, or we've looked at every possible case and indeed it succeeds. And so there's classic kind of vulnerabilities in computer systems, and I'll just mention them for those of you who are familiar with this sort of world. Buffer overrun, checking array bands. Sometimes if you're saying, go to an element of an array, if you go off the end, some programming languages don't check that, and then you can mess up the underlying computer system and do something with it. So you'd like to analyze a program to make sure that it never messes up its arrays. sequencing the calls from an application programming interface, an API, and making sure that before I call the main one, I set the initialization up, and then I call the main one, and then when I'm done with the main one, I call the ones that are supposed to pull it down. So that's, many of us who are slightly older in this room will remember Microsoft's blue screen of death, like happened all the time. That was mostly because drivers and other code that people put on it didn't respect the API sequences, and they called the APIs in the wrong orders, and that provoked that kind of error. Now, all of those drivers get checked, at least the ones that Microsoft approves. They get checked with stuff that is built right on this mathematics with these kinds of tools. So, the point that I'm trying to make is first wave is still tremendously powerful, tremendously relevant, and there's a rich world. If you wanted to Google a space to explore, the phrase formal methods is an interesting phrase to look at, formal methods. And that's the techniques of using this sort of mathematics to be able to say something rigorous about the nature of software. However, first wave has its major limitations. And one of the times that this was really clear was when DARPA was doing an earlier grand challenge, the self-driving car grand challenge back in 2004. So what they'd been doing was getting some teams around the US to look at the idea. Various people had stuff that does vision, some people had done stuff which did tracking and other aspects of driving. Can you put it all together to do a self-driving car? So you might think self-driving cars are just around the future, just around the corner. But we've been working on it maybe for 20 years, close to 20 years at this point. So back in the Grand Challenge in 2004, these vehicles, they had 140 miles of desert road that they had to track. That first year, no vehicle got to the end of it. In fact, the furthest any of the vehicles got was about 8 miles down that track. And the challenge was that they would be driving along and there's some dark area in front of you. Is that dark area a rock or is it just some shadow? What's the rule that you would want to write in a rule-based system to say whether a dark area is actually something that you have to drive around or whether you can just drive straight through it? I mean, it's pretty tricky, right? It's hard to think about that. The next year, many more cars finished. 5 of them finished. This was the winner of it. And one of the key differences that happened was instead of just relying on handcrafted knowledge, they started to use statistical techniques to be able to say, does it look likely that this is a dangerous thing or something that I can go through? And again they were using various statistical techniques in an area that's now called probabilistic programming, and I'll talk about that a little bit later on. So this had a big impact on a number of people to say we need to really push in this area. And this led to what is often thought nowadays as AI, because people tend to discount the first wave, even though, as I've just argued, you shouldn't discount the first wave. This second wave of AI, I like to think about it as statistical learning. People often say, oh, the machine will just learn something. And that's not true at all. There's actually a lot of rigor, a lot of engineering, a lot of mathematics that goes into how these things work. And so examples of them are face matching, or Siri, or those of you who might have followed AlphaGo, or any of those kinds of things. They're all using these techniques from statistical learning. So here, what happens is, as I say, it's not the case that engineers, it's not the case that the machine, you just set it at a problem and it learns. What you do is you build a big statistical model that you think is probably the right sort of size and shape to be able to make the distinctions that you want to make. And then you throw a ton of data at it, and based on that data, the millions of parameters of that model just get tweaked and tweaked and tweaked and tweaked. And if you were right that the overall structure was good, then that trained model will start being good. So let's dig through those techniques and see how they work a little bit. Before we do, just say something about what we've learned on the second wave of AI. Turns out that using these statistical models, you can build things that are really good at perceiving data, making sense of data, because you've tuned them on tons and tons of data. And so now if you give it more data, the model itself is rich enough, it's multidimensional enough, that it will be able to sort of essentially pick an echo of stuff that it's seen before and be able to figure stuff out. And it's really strong on the learning because you train it through data. It's interesting, however, that the reasoning capability of these models is way down. Like trying to program a chess computer with a neural net, one of these statistical models, it's not at all clear even that you could do that, because there's something about the way a chess program works. I mean, maybe you can now that we've seen how to do AlphaGo, but typically these things are not able to do chain reasoning. If this, then that, and then this other, let me bring all of that piece of information together. And again, abstracting, taking what you've learned in one situation and applying it in another situation. They don't really have techniques there. So I'd like to talk a little bit about the fundamental mathematical ideas that underpin this kind of way of thinking about AI, of these statistical models. And I'm going to use a scary word at first. There's something called the manifold hypothesis. So we're familiar in geometry of being able to do triangles and squares and things like that. And for a long time, thousands of years, people thought that geometry was you take an infinite flat plane like this floor and keep it going, and then you do stuff in that structure. And so if you have two parallel lines, they will always be the same distance apart. And in the history of mathematics, people tried to demonstrate that that parallel line one was always going to be the case, and they just discovered that you could actually tweak the nature of geometry itself. And so there are geometries in which parallel lines actually meet one another. So a great example is, think about the geometry of the surface of a soccer ball. So you've got a soccer ball, a smooth soccer ball, not with all the creases in it. So take a perfect sphere, and now imagine doing geometry on the surface of a sphere. So first of all, you have to say what a straight line is, because it's a slightly strange concept. Well, a straight line on a sphere is something where you don't deviate to the left or the right, but you just keep going. Turns out that the straight lines are exactly the great circles, the full circles. If you're off center, then you're actually twisting around to one side or the other. So straight lines are the full circle. So it's now impossible to have any two lines that are not the same line and not have them cross. Any two full circles will cross. So even though two lines might be completely parallel at one point, they will later on cross as they come over. How many degrees in the vertices of a triangle? Well, we all know the answer, 180 degrees. Except if you're on the surface of a sphere, well, it depends where that triangle is. So imagine the sphere where you start at the North Pole, you come down to the equator, and then you go a quarter of the way around, and then you go up at the top. You've got three angles which are all 90 degrees. So those that adds up to 270 degrees in a triangle. So it turns out that the geometry of geometry changes when you're on a different shaped surface. And these differently shaped surfaces that feel like they're flat when you're small enough, but when you get large, you start to see the shape of them. They're called manifolds in mathematics. And there's a whole branches of mathematics study the nature of these manifolds. So here's a hypothesis about natural data. That natural data sort of clumps together in interesting ways, that it forms lower dimensional structures like manifolds that have intrinsic geometrical structure, even though they're embedded in a huge data space. Now, there's a lot on this slide, and we're going to unpack it sort of piece by piece as we go through it. So don't be afraid of this slide. In about 10 minutes, you'll say, got it. I now understand what was on that slide. So, a manifold is a geometric space, a connected geometric space, where small changes in the value are probably insignificant. If you start making big changes, then they start to become significant. There's no hard and fast line which says insignificant, significant. It just, like, the more you get away from it, the bigger the change is. Like, have you ever thought of a pile of sand? Like, if I've got a pile of sand and I take a grain of sand away, I still have a pile of sand, right? So I can do it again, and I still have a pile of sand. I could do it again, but at some point I will no longer have a pile of sand. So there's something interesting about the nature of insignificant things, even though when they add up, they become significant. So